Hello guys, welcome to my second video tutorial, which is following the first video tutorial that we have looked at starting from the IGCSE curriculum. We basically, just a quick recap, we looked at how to convert binary into denary and then how to convert denary into binary. This video tutorial is following what we've learned last time, and we're going to be looking at the different type of memory sizes of computer systems that we have. We have started talking about the binary system, and we said the binary system is basically represented by bits made up of ones or zeros, and we also talked about 8 bits making up 1 byte, and the byte is usually the smallest unit that we have in the computer memory. Now we're going to be looking at the different type of memory sizes that we have, looking from smallest to highest of a computer system. And of course we're going to be looking at the equivalent of those memory sizes from their particular memory size into bytes. So remember last time I mentioned that 8 bits make up 1 byte, and usually instructions for computer systems, because they only understand machine code, which is basically bits of ones and zeros, those instructions are usually stored in something called a register, which we're going to see today, which you can find on the microprocessor of any control system for any digital device. So it's very important for the computer system to have instructions interpreted in binary, because the computer is digital and only understands ones and zeros. So looking at this table 1.1, and just a quick reminder guys, I'm using the Computer Science IGCSE textbook, and right now I'm on page 14. So looking at the table on 1.1, we see that the smallest memory size we have is 1 kilobyte, and that is equivalent to 1024 bytes, and it goes on to 1 megabyte, which is equivalent to 1,048,556 bytes, and we go on to 1 gigabyte, 1 terabyte, 1 petabyte. So basically this table is a hierarchy of the memory size, starting from the smallest unit of memory size, or the smallest memory size in this case, which is 1 kilobyte, up to the largest, which is 1 petabyte. Now, what we understood is a typical data transfer on the internet is usually 32 bits, which means about 4 megabytes per second. And they give a very good example saying if you wanted to transfer 14 megabytes of a file, that would take you 10 seconds to transfer. So again, depending on the memory size, the smallest it is, the slowest the data transfer, of course, as compared to a larger memory size, which can transfer or stream data online. The same thing goes for a computer system. If you look at your hard drive or your memory space on your computer system, or even your RAM memory capacity, and you have a 4 gig RAM, it's usually faster than you would say a 128 MB RAM. So just giving you a random example there just to point out how these memory sizes work. So we're going to be looking at the IEC Convention, which is now adopted by some organizations, and this basically shows again the different type of memory sizes we have and their equivalent bytes. So in a denary system, so you notice that we're using this base 10s because we're representing the equivalents for these memory sizes in denary system. So 1 kilobyte is equivalent to 1,000 bytes, 1 megabyte. So it's very essential for you guys to remember these things because they do ask them in past papers. And as we go on in this channel, I will be doing video tutorials. The web will be looking at past paper questions, and you'd see that they would ask you to interpret or convert one memory size into another, or to interpret what the memory size meant. So it's important that you understand this part. So 1 kilobyte is equivalent to 1,000 bytes, 1 megabyte is equivalent to 100,000, that's 1 million, sorry, bytes, and 1 gigabyte, and then 1 terabyte. So it keeps going on and increases in size from smallest to highest. Now, so the IEC Convention, which is an organization that is used to basically create or store and display memory size and storage capacities. They also have displayed the memory size for computer internal memories, including the RAM. So here it starts. So this memory size that we're looking at from kilobyte to terabyte is basically for internal memories of the computer system. So they don't represent the storage devices or external memories or hard disk drives. This is just basically for the RAM, the ROM, the processor, etc. So 1 kilobyte is equivalent to 1024 bytes. 1 megabyte is equivalent to, again, 1,048,576 bytes. And then 1 gigabyte is equivalent to 1 billion, and then 1 terabyte. So it keeps going on and on and on in terms of increasing size. So anytime you see a kilobyte and a terabyte, for example, you know that they're referring to the computer internal memory storage, which includes RAM. So now we're going to enter the main business for today, and the main topic that we're focusing on to understand today is examples of where do we actually use binary realistically. So I did mention in the first video tutorial, and I said binary was the language of the computer system. It's represented by ones and zeros. The computer only, understands machine code. So even when you program in Java or Python, those are high-level languages, and they need to be interpreted using a compiler into machine code so the computer can process information. The same thing goes for control systems, and control systems will be like robotic systems or anything that would need to perform something automatically like a washing machine, a dishwasher, a microwave. So all these control systems must have instructions that they need to follow. So they're programmed with instructions that they need to accomplish or to follow or to do. And those instructions are usually stored in registers, and registers are made up of bytes of instructions, which is made up of bits of ones and zeros. So here we have 1 byte of instruction, and we can see that we have different multiple bits of ones and zeros. So if we were to use this as an instruction for a particular control system, remember that digital systems and control systems have microprocessor chips, which basically are the ones that are used to control the system with the help of registers. So these registers would essentially be found on these microprocessor chips. Now, it says when computers or microprocessors are used to control devices such as robots, registers are used as part of the control system. The following example describes how registers can be used in controlling a simple device. Let's take example for a robot vacuum cleaner which has 3 wheels, A, B, and C. So the A wheel rotates on a spindle to allow for directions, which means forward and backward. The B and C wheels are basically fixed and revolve around the axles to provide only forward and backward movement. And they have an electric motor attached. So here's an example image of a vacuum cleaner, and we have the first wheel, and then we have B and C wheel. So these are the wheels that we find on the vacuum cleaner. Now, your typical vacuum cleaner in your home, if you were to use that vacuum cleaner, whenever you press a button and you wanted to move it forward and backward or right or left, it's supposed to move in that direction. But how does it understand? You're just pressing the button, but the computer is digital and does not understand analog data, does not understand buttons being pressed. What it does understand is basically binary data, and that's made up of ones and zeros. So an 8-bit register is used to control the movement of the robot vacuum cleaner. So we're going to be looking at this 8-bit register, which contains instructions for this vacuum cleaner to be able to perform, functions like move forward, and it moves forward and you can vacuum, move backward, move sideways, left, right, and so on. So this register is essentially where the instructions for this vacuum cleaner will be stored in bits of ones and zeros. So here we have the first one that says motor on. I'm going to write this down here because I think it's going to be easier when we try to explain this. So I'm going to write the topic for today, which is registers. And we're going to be looking at those examples that we have in there. Registers. Okay. So we're going to go to the first one that says, so I'm going to change pens here, and I'm going to do motor on. So I'm going to try to maximize my space as much as possible. I'm just going to write motor B, so that would mean motor B. And next we have motor B again. So I'm writing this out, guys. And then we have motor C, motor C. So motor C. And then we have motor C. And then we have B direction forward and B direction backward. So I'm just going to use short acronyms for that. So I'm just going to say B forward as in FWD, and C, I guess that's going to be B backwards, sorry, not C. So B backwards, so BWK, and then C forward, C backwards. So I'm going to really try to maximize my space here. And C backwards. Okay, So guys, we have motor B, motor B, motor C, motor C. Here we have forward direction, we have backward direction. Let me just redo this because I think it's not very clear, so I really want this to be clear. So I'm going to write B, F, D, so that means forward, guys, in case if you're wondering. And then B again, BK, that would mean backwards. And then C, FD, that would mean forward again. And then C, BK, that would mean backwards. Okay, so I'm gonna just write it here. So FD means forward. And BK means backward. Just as a very quick kind of map out so that we remember this and we don't get confused when we're looking to interpret this register. So this is forward and this is backwards. Okay. All right, I think here would be a D and an R. Okay. So now we're going to interpret this whole register we have, the instructions in this register, using binary. So B is motor on, so this means on, so it's going to be on. So this is motor B on. The next one means motor B off, okay? And then the next one, motor C, and that is on as well. And then motor C is off as well. And then of course we have the next one, which is going to be B forward, so we don't need to do anything there, B backwards, and then we have C forward, C backwards. So B forward here, B backwards, C forward, and C backwards. Now, if this vacuum cleaner that we've seen in figure 1.3, if we wanted to pass an instruction to this vacuum cleaner to either move forward or backward or move right or left, how would we pass the instruction in the register so that when a particular button is pressed on the vacuum cleaner, it's supposed to do an action? So first, we have this instruction, so we're pretty much going to use this instruction. The first one goes for 1. So 1 is under here. Remember that this is an 8-bit register, guys, so it's really essential that you recall this is an 8-bit, so it's typically a 1 byte, so basically there are 8 spaces in here. So it contains 8 bits of ones and zeros. So I'm just going to represent that in boxes. I feel that's going to be easier for us to comprehend because then we can easily put those numbers in there. So these are 8 bits registers that contains instruction for the vacuum cleaner. So this is the 8-bit. So the first instruction starts with a bit of 1, and then it goes to 0. And then motor C has 1. And then motor C is off, so it's 0. Well, 0 is what we have here. So 1, 0, 1, 0. And then we have 1, 0, 1, 0. So it keeps getting to 1, 0, and then 1, 0. So let's make sure. So we had this instruction, and we want to interpret this using these set of instructions. They kind of look like mnemonics so that the register can be able to perform an action by looking at binary. So what we're doing here, the objective is to explain or to understand how we use binary in control systems to pass on instructions from humans so they perform an operation. And these control systems would mean robotic systems or digital systems. So we have 1, 0, 1, 0, so that's pretty much what we have, 1, 0, 1, 0. And then we have 1, 0, 1, 0. So again, we have our 1, 0, 1, 0. Now, what do we understand by this? Let's just make this clear that 1 is going to mean yes, okay? Remember that I said the computer understands a 1 either as a yes, a 0 as a no, a 1 an off, or 0 as a 1 on and a 0 on, depending on what system you're using or what instruction you're passing. So for this particular instruction that we're doing, we're going to say 1 means yes and 0 means no. So motor B on, we have a 1, which means yes, turn it on. Motor B off, we have 0, says no, don't turn it off. Motor C on, it says yes, 1, so turn it on. So we know that motor B and C are on. Motor C off, it says 0, which means no, don't turn it off. Now motor B forward direction, it says yes. So B is turned on, if you remember the first instruction, and it's moving in a forward direction. Motor B backward direction, it says no, so it means it's not moving in a backward direction, but it's moving in a forward direction. Motor C forward, which means 1, so that's going to be yes, it is moving forward. So it was turned on initially here. Motor C was turned on here. And now we can tell that motor C is also moving forward. Motor B was turned on here, and we can tell that motor B is also moving forward. So that tells us the two wheels are actually moving forward. And finally, we say motor C is 0, so it means no, so it's not moving backwards. Sorry, motor C backwards is 0, which means no, it's not moving backwards. So what's the conclusion? What's the result? The result is the instruction that the vacuum cleaner is going to understand is that motor B and motor C are on. So motor B and C are both on. And then the other instruction is going to be, so I'm going to write it there. So motor B and C are both on. That's the first instruction. The next instruction is motor B and C are moving forward. So I'm going to just write motor B and C. So that's my and, guys, in case if that's not too clear, but that's like an and symbol that I'm trying to write there. So motor B and C, I'm going to write it at the bottom here, are forward. So I'm just going to write FD, which would mean forward. So motor B and C are both on, and motor B and C are forward. So basically, they're moving forward, sorry. So basically, that's the instruction that the vacuum cleaner is going to understand. Let's say if you press the button A on the vacuum cleaner. So let's say if you have a button A and it's pressed, it means that this instruction would execute, turning motor B and C on and making them move forward. So that essentially would say that they're effectively the vacuum cleaner, is moving forward. Now they give us a classwork and they said, what will be the effect if the register contained the following values? So we're going to be erasing what we have here. So because we're going to input new values in this register, remember that this register contains instructions, and these instructions are executed based on whatever binary bits is present in the register, so and whatever button is pressed. So each button is to execute a particular instruction. Button A is to make the vacuum cleaner move forward, which is what we just see now. So let's say another button is pressed on the vacuum cleaner and we have a new instruction. So we're going to interpret this instruction and see what it means. So I'm going to write down again, I'm going to adjust this right here. Okay, and then continue. So our instruction is if we had 1, 0, 0, okay, so that's what it says. We're in activity 1.3 now, guys. Last time we did 1.1 and 1.2, so now we're on 1.3. If we had 1, 0, 0, and we had 1, 1, I think that's it, right? And then we have 3 zeros at the end. How do we interpret this instruction? So again, we know that 1 means yes and 0 means no according to the instruction we have here. It depends, again, it can change to on and off. Again, the computer just understands ones and zeros. So looking at this new instruction that is put into this register made up of 8 bits, we're going to interpret it. Motor B on, and it says 1, so that means yes, motor B should be turned on. Motor B off is 0, says no, it shouldn't be turned off. Motor C on is actually 0, so it says no, it shouldn't be turned off because, 0 is representing no. Motor C off, it says 1, it's yes, it should be turned off, so it's still off. Motor B is moving forward, there's a 1, which means yes, it should move forward. Motor B backward, it says no, so it means it's not moving backward. Motor C forward, it says 0, which means no, it's not moving forward. And motor C backward is no, again, it's not moving backward because it's not even turned on initially, so it can't move in any direction. So what is our conclusion by looking at this binary number and interpreting? Our conclusion is that motor B is turned on, right? Because we first had that instruction from the beginning. So motor B is on, and it's moving in a forward direction, because we also had that, saying yes with the 1 bit that is represented under that instruction. So motor B is on and it's moving in a forward direction. So I'm going to write that down. And it's moving forward. Oops, there it is. I guess I utilized my space. All right, so again, forward as in FWWD. So motor B is on. From this instruction, we can tell motor B is turned on because it says 1, and it is moving in a forward direction. All right, so that's the conclusion, guys, for this this instruction, which is activity 1.3i. So I'm going to leave you guys to practice doing 1.3i. It's pretty much the same thing. The easiest way you can go about doing this is creating a table where you have your instructions, as in motor B on, then moving forward, moving backward, because that's going to be easier, like what we've done now. So you can easily put into these, under these instructions in the register, you can basically put the binary digits. So I want you guys to try to be able to do the remaining ones, which is 1.3, activity 1.3 I, and I, third one. We're going to move on into the next thing for the next activity and see what we need to do on 1.3. So I'm just erasing this so that we have a clear screen. Okay, so let's fix our table. Again, this is an 8-bit table, guys, just to remind you. Okay, so we are in activity 1.3. We're still there. We still have to look at another example of a different question, right? So try to do these two on your own as a practice work, like what we've just done now, to interpret this binary register using the instructions that we had. Now we're going to be looking at this verbal instruction or verbal question scenario. It says, what would the register contain if only motor C was on and the motors were turning in a backwards direction? So motor C should be turned on and it should be turning in a backwards direction. So, and the motors, so it doesn't say only one motor, so that means B and C should turn on in backwards direction. So basically what they're telling you is, looking at this scenario, interpret this scenario into binary digit made up of 8 bits, like what we did. So instead of actually interpreting this binary digit made up of 8 bits into an instruction, we now have an instruction and we need to interpret it into machine code, machine language, which is made up of binary bits of 1s and 0s, so that the vacuum cleaner can understand what to do. When you verbally say, or as a human, when we say this instruction, the computer doesn't understand text, so this has to be interpreted into machine code using binary. So how to interpret it? It says only motor C should be turned on. So we know that initially we said, I'm going to erase this part here, guys, because it's interrupting where I need to write. I think I'm going to put this at the top. That's going to be way easier. So I'm going to put this at the top right here, and this is instruction activity 1.3, sorry. So only C should be turned on, motor C should be on. So B on, that's going to be 0. It should not be on, right? So that's going to be a 0 because they said only C. So remember, 0 represents no. B off, that's going to be yes. It should be off, so 1. C on, that's going to be a 1 because it says only motor C should be on. C off, it should be a 0. No, it should not be off, it should be on. And they said the motors were turning backwards in a backwards direction. So B forward, we're going to say no, it shouldn't be forward. B backwards, we're going to say yes, it should be backward, because they didn't say just the motor, they said motors. So it's not just C, it should be B as well. So B forward is 0, no. B backward is yes, 1, because it's supposed to turn in a backwards direction. C forward is going to be yes as well, because they said motors, so B and C. And C backward is going to be a 0. So this is your binary interpretation after you've been able to look at the scenario and interpret it, saying if only motor C was on and the motors were turning in a backwards direction. So these two motors will be turned in a backwards direction. Oh, guys, I'm so sorry. I made a mistake here. This is not supposed to be 1 because it's supposed to turn in a backwards direction. So I put it as forward. So motors were turning in backwards direction. So motor forward, C forward, sorry guys, it's going to be 0 because it's not supposed to be forward. C backwards is going to be 1. Yes, it's supposed to be backwards. So that's what I made a mistake there. Sorry about that, didn't see it. So motor B is on, it says no. Motor B is off, it says yes, it should be off. Motor C is on because it only says only motor C should be on. So motor C is on, yes. Motor C is off, no. B forward is no, B backward is yes. C forward is no, C backward is yes. So this is the final binary instruction that we get made up of 8 bits that is going to be stored in a register so that the robot, the vacuum cleaner, could be able to perform an instruction. So the last part is this one here. So it says, what would be the effect if the register contained the following? Obviously, what would happen if the register had all of the instructions as yes, 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 and yes. So what will happen is you're saying motor B on, motor C off, yes. Motor C on, yes. Motor C off, yes. And then you're saying, so it doesn't make sense because it's going to be an error obviously because you're saying it should be on at the same time you're saying it should be off. You're saying move forward, you're saying move backward for 2 of the motors. So eventually what we're going to get from this instruction is an error. So you're going to get a system error and the vacuum cleaner is not going to work because obviously it can't work with this instruction. So the next one is the hexadecimal system, and this is different from the binary system. It is a base 16 system from the word hexadecimal. It is the system that we use to represent each key on our keyboard using a hexadecimal number or code. So we have keys on our keyboard, whether you have a QWERTY keyboard or you have an AZERTY keyboard, depending on whatever language you prefer to use. But those keys and symbols that we have on our keyboard have to be represented by some sort of number or code, which will be interpreted into binary, and that's computer language whenever you type in a key. So hexadecimal system, one of the main uses of hexadecimal systems is in the ASCII table, and the ASCII table basically contains the keys and also contains the symbols on our keyboard, interpreting them into hexadecimal numbers, which basically get interpreted easily into binary. So we represent all the keys and symbols on our keyboard using hexadecimal numbers. So to understand this hexadecimal system, we know that it's not a base 2 like binary, but it's base 16. So we're going to be looking at the powers of 16, and we also know that it is represented as 4 digits. So 16 different values are used to represent each digit. So because the system is based on 16 different digits, they normally start from 0 to 9 and basically A to F. So what I mean is, if you go here, we're going to use a new slide. The hexadecimal system, is represented using numbers and alphabets. So we're going to see that, hexadecimals. So basically, we start to represent 0 in hexadecimal as 0. So in a denary system, we have 0. So I'm going to write denary at the top here. But in a hex system, we have it represented as 0, sorry. The same thing goes for 1. We represent it as a 1. The same thing goes for 2. We represent it as a 2. 3 is represented as a 3 in hexadecimal. 4 is represented as a 4 in hexadecimal. 5 is represented as a 5 in hexadecimal as well. So it keeps going until you get to 9. 6 is represented as a 6 in hexadecimal. 7 is represented as a 7 in hexadecimal. 8 is represented as an 8 in hexadecimal, and then 9 is represented as 9 in hexadecimal. However, when you get to 10, it's now changed. So 10 is not represented as 10 in hexadecimal, but rather it is represented as A, alphabet letter A. 11 is represented as a B. Oops, sorry about that, guys. My arrow just... And then I'm going to erase that and do it one more time. So 11 is represented as a B, and then 12 is represented as a C. So we're going to redo this. 11 is a B, then 12 is a C, 13 is a D. So these are these numbers representations in hexadecimal. 14 is represented as an E, and it pretty much stops at 15. And 15 is represented, as you can already tell, as an F. So these alphabetical characters are representing numbers from 10 to 15, but everything from 0 to 9 pretty much stays the same with hexadecimal systems. So what we need to know is the powers of 16 that go from 16 to the power of 0 up to 16 to the power of 4, because with hexadecimals, they're usually represented by 4 binary digits, not unlike binary where you have 8 different bits to represent a binary digit. So I'm going to be stopping this video tutorial here, guys, and I'll continue this in our next part video tutorial on hexadecimal systems and the conversions from binary to hexadecimal, hexadecimals to binary, and so on. So I'll be seeing you guys in our next video tutorial. Please make sure you share this amongst your students or friends or anybody who's having difficulty understanding these topics in IGCSE. I'd love to hear your comments or suggestions if you have any, and I'll see you guys in our next video tutorial. Have a great day.